I'm going to get started. I know you guys are still printing a few off here, but I'm going to start with this first slide here. You guys remember from yesterday, identities are like equations, but they're not equations that we intend to solve. It's an equation that we've discovered is true in all scenarios. It doesn't really matter what value you plug in for x. Both sides of the equation will be true, whether you plug in 1 or 17 or -2. I guess there is one exception. If it makes it become like something divided by 0, that would be the only number that doesn't work. What I'd like to do today basically is introduce you to the remaining identities that we didn't really use yesterday. For the most part, like if you understand how they work, they're just equations you can use to substitute for, I don't know, puzzle solving. That's really what you're going to be given in this section here. I don't think any of these problems are particularly real-world problems. They're just puzzles to solve. So, let me walk you guys through the sum and difference identities. These are the ones where you have actually more than one variable. So you're not just going to have x, you're going to have a's and b's, meaning you have like more than one angle. So here's a question I want to start with. The sine of a plus b, is this kind of like foiling? Are you able to just FOIL this out and kind of have the sine of a and the sine of b? Is that something that would be true? So I'm just going to test it. Give me a number for a.
2.
Sure. And a number for b.
9.
Sure. So what we need to do is figure out whether the sine of 11, because that's what 2 and 9 is, right, is equal to the sine of 2, and then later we have to add the sine of 9. We're going to see whether these two things are actually equal to each other. So we'll just test it out. Sine of 11. It doesn't even matter whether you're in radians or degrees. That's what I got. And then I'm going to do the sine of 2, and I'm going to add the sine of 9. And hopefully you'll agree with me those things are not the same as each other. So the first thing I need for you guys to know is that the way that sine and cosine and tan and those two things work is that it is not like foiling. You don't go like sine of a plus b and FOIL out like the sine to each of those things. That's not really what's happening here.
So we stay in radians or is it?
Well, you could be in radians or degrees. Either way, it shouldn't be true. Like you can't have sine of 11 be the same as sine as 2 plus 9. That's not going to work. So, if you were in radians or degrees, it wouldn't equal. What we have discovered are a bunch of other identities that are true for adding and subtracting. I can't probably show you where these came from until we learn some calculus. So a lot of these have been derived using calculus formulas. But honestly, it's no different than what we did last day. I mean, so long as you just understand how to substitute and just use a formula, I feel like it's very much like physics in a way. Where it's like, here's some formulas. Use them, I guess. So I don't really have a lot to add other than let's just try some examples here. Let's try to find the exact value of this. Now you could type this all in your calculator. Or maybe you'll recognize, hey, sine, cosine, cosine, sine, that is one of the rules off of your formula sheet that's on this slide here, where you have like sines and cosines and cosines and sines. See how you've got sine, cosine, and then you're adding cosine, sine? That is sine, cosine, adding cosine, sine. Does that make sense? Well, if you have this set right here, it's really the same thing as adding your angles of sine A and B. So this is the same thing as the sine of 40 and 20, which is 60. Isn't it? And then sine 60 should be something that we can do an exact value for. Because we have like a special triangle that goes 60 in the corner, 1, 2, root 3, and sine is the opposite over hypotenuse. Does that make sense? If you wanted to double check this, I guess you could type in sine 40, cos 20, cos 40, sine 20. You could type that all in. It would give you some decimal number. And that decimal number should hopefully be equal to whatever root 3 over 2 is. I want to think that's like 1.15 or something like that, or 0.866. I have them memorized. I just don't know which one's which off the top of my head anymore. Any questions on that one? Let's try the next one. You need to look for some sort of rule that involves a cos adding a sine. So going back here, the one that involves a cos sine is the a minus b. So we need to do the cosine of the first one, which is 7 pi over 12. We need to minus pi over 3. As I look at this, are we able to find an exact value of something like this at this particular moment? I'd say no, not yet. Oh, go ahead.
Okay, so from formulation, we're looking at what it says.
Yeah.
Cosine, sine, sine.
Yeah.
And this one says, I can't
You good? Okay. Good,
I
I'm glad though.
I got confused about the subtraction. That's all.
I don't. That's the worst feeling in the world. Okay. Okay, everyone good with this till this point right here? You can't actually find an exact value unless you find some common denominators. And these guys don't have common denominators, but I can change pi over 3 to being over top of 12. But that means I have to times everything by 4. So really pi over 3 is the same thing as 4 pi over 12. The reason why that works is then you can actually subtract these things. Now it's the cosine of 7 minus 4, which is 3 pi over 12. And 3 pi over 12 is actually something that can be reduced back down again. 3 and 12 are both divisible by 4, I guess. So it's pi over 4. And then hopefully you recognize that a pi over 4 is one of these guys. So the answer is 1 over root 2. Or they might write it as root 2 over 2. You guys all familiar with the way to change this one to this one? Just in case they write it in the other format. Should I talk about that? Yeah, you're timesing it by the square root on the bottom and the top. Because then the root 2 becomes 2. And then the top just gets the root 2. Okay. For sure. I'll just get rid of that little section there. But that's what you're doing is I'll put it in a bracket instead actually. That's what you're doing if you want this answer. We can actually use it to solve for an exact value of something that you wouldn't expect. For example, this one right here, we can actually find its exact value. And so you might start off by saying, Chris, how can we possibly do this? We can only do exact values for things that are divided by 6s, 4s, and 3s. But if we work backwards and find a way to split this guy up into things that are 6s, 4s, and 3s, then we can use one of our identities to do that. Let me see if I can show you how here. 13 pi over 12 would be as though like you broke things up into over 12s, 2 different things over 12s. And I think you should be able to do this by doing a 4 over 12 and a 9 over 12. So what I'm actually doing here is I'm breaking it up backwards into 2 different pieces. How you would figure out which pieces to break it up into, I don't have a great way. I know the answer for this one, so I can show you it. But like if you're wondering like how I chose the 4 and the 9, that's what makes the question so hard. Is you got to try to find 2 sets of numbers that work. Because the reason why I chose these numbers is although they're both over 12, they now can be reduced into something that's either over 4, over 6, or over 3. That makes sense. Like for example, now what we have is this is pi over 3. And 9 over 12 is actually 3 over 4. So I found a way to break up something over 12 into 2 different pieces, each of which is something that we can exact value because it involves things divided by 3s, 4s, or 6s. Now we need to use the rule for cosine of adding. So you guys have your sheets closer than I do in terms of looking at it. What's the cosine rule for adding two things?
Cosine A, cosine B minus sine of A.
So cosine A, cosine B minus sine A, sine B? Is that correct? Okay, so then I'm going to rewrite this out using that formula. So it's going to be the cosine of the first thing, which is pi over 3. It'll be the cosine of the second thing, which is 3 pi over 4. Then we're going to subtract the sine of the first one and the sine of the second one. Now we need to draw out a couple of angles. Put it up here. I'm going to do the pi over 3 one first, because pi over 3 is a little easier. Pi over 3 is 60 degrees, which is this 1, 2, root 3 triangle. So I need to use that for this one here and for this one here. So I'll do those in red, and then I'll do something else in another color later. What is the cosine of pi over 3 according to this triangle? 1 over 2, adjacent over hypotenuse. So rather than writing cosine pi over 3, I'm going to write 1 over 2. And then over here, here's the other angle that requires pi over 3. But it's sine of pi over 3. So sine of pi over 3 is the root 3 over 2. So I'll use another color for the other ones just to help keep it straight. We're going to go Christmas theme today. Red and green. All right, where would 3 pi over 4 lie on a triangle? Right here? Yeah, that's where 3/4 of pi is. Because I know this isn't perfect because it's obviously the wrong angle, but like this would be the first quarter of pi, second quarter, third quarter, fourth quarter. So that's pi over 4 sitting in the corner there, which makes that a 1, 1, and a root 2. The only twist I have to make sure I catch, though, is that since it's sitting in quadrant 2, this is a -1. So then what's the cosine of that? Well, it's the adjacent over the hypotenuse. And what is the sine of that? The opposite over the hypotenuse. Does that make sense where those values came from? Okay, so I'm just going to put this together then. What you have over here is a -1 over 2 root 2. And then in between we're subtracting. So then we're minusing root 3 over 2 root 2. So my final answer as an exact value would be like this: -1 minus root 3 over 2 root 2. That is the exact value. It worked out really conveniently that these things had denominators that were the same already. So I just kind of left them. That just means I have to take the top and subtract them. So -1 minus root 3 all over 2 root 2. So that is the exact value for this. Okay. I think it's working. We've been using it for the last little bit. Okay. Any questions on that? Okay, if this were me, by the way, on a diploma, I would just type this in my graphic calculator. You'd get like, I don't know, 1.32 blah, blah, blah. It's not the answer, obviously, right? And then if it was multiple choice, I would just type this in my graphic calculator. And if I also got 1.32 blah, 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 then that's your answer. The only downside, if they do this, is if they ask you to answer it like this, -a minus negative root b all over c root d, and they make a numeric response, then it sucks. However, they did this one year. I think I told you this story. Guess and check random numbers. I know it seems kind of silly to do, but like you could check like, 1 and 2 and like, does that make sense? Like you know that the numbers have to be whole numbers. They're probably not going to be like 7, 8, and 9. So you could, if you needed to, and you're absolutely stumped, you could just try guessing and checking 1s, 2s, 3s, maybe 4. Maybe not 4 actually, because 4 square root's down to 2, so it probably wouldn't be 4. Does that make sense? So. Sure. Back up here.
Oh, okay, so the angle, the pi over 4,
Yeah.
where'd that come from again?
Well, because we were looking for 3/4 of pi. So 3/4 of pi is all the way around to here. This is like your first quarter, second quarter, third quarter of pi. So the angle from the 0 line all the way to here is 3/4 of pi, which means that it's just a 45 pi over 4 in this triangle. That makes sense? Okay. We can do the same thing. I feel like in the interest of time, I'm not going to solve the whole question. I'm just going to solve part of it. We need to try to find a way to break 345 up into angles that we can work with. Anyone have any ideas which ones we can break this up into? Because that's probably the most challenging section, is we need to make this a sine of something. Now, if we're doing this in degrees, it needs to be something that's either a multiple of 30 or 60 or 45. What did you say?
165 and 120.
120 is not bad. 120 is something I can work with. Not convinced 165 is useful, though. Because 165 would be an angle sitting over in this quadrant right here with 15 degrees remaining. And that's not something we have an exact value for.
Yeah.
Any other ideas?
So wait, what are we trying to do?
Well, we're trying to break 345 up into two different numbers. And we want those two different numbers to be like something we can use on an exact value triangle. This is probably the hardest part of the question, is just trying to guess and check what's useful. So like, well, let's just start at the beginning there. What happens if you did like, say, 60 degrees? If you took 60 degrees off of 345, then you'd be left with, what would it be, 285? 60 is useful, 285 is not. So try again.
Maybe 120 and 225.
What did you say?
120 and 225.
120 and 225. 120 is useful.
225 is 180 plus 45.
So 120 would be in this quadrant right here, which would be a 60 degree in the corner. We can work with that. And then 225 would be in this quadrant right here, with a 45 in the corner. That'll work. It's not the only answer that would work, but that one would work if you wanted to keep following that out. There's another one I can see. You could do 45 degrees and 300. Yeah. Well, sometimes it just takes a little while to get used to what in theory might work, right? So if you had to do that one, then 45 degrees would be sitting over in this quadrant right here. And the 300 would be all the way around to here, which would have a 60 degrees left. So then all you have to do is break it up into whatever the sine rule for adding is, and then go from there. But let's move on if you guys are okay with that. We can do that if you want.
Oh, wait.
Okay.
Sorry. I wanted to draw that.
One last set of identities that we haven't talked about are called the double angle identities. And then I think after this I've covered them all, and then I've just got a bunch of diploma questions to track. So in double angle identities, what we'd like to pretend is, let's say that like A and B right here, say they were the same number. Say that it was the sine of 15 plus 15. Like if A and B were the same thing for some reason. Well, what that would end up happening here is then you'd have the sine of 15 times the cosine of 15. And you'd have the cosine of 15 and the sine of 15. And what I'm trying to get at here is, do you guys see how those two things, although they're written in the wrong order, it's the same thing written twice? Does that make sense? So what you could then say is that you have 2 sine 15 cos 15. And over here you could say that you have sine of 2 15s. And based on this logic, this is where the next identity came from. which looks like this. The sine of 2 of A is equal to 2 sine A and cosine A. So we're back to only having like one variable rather than A's and B's. We just have A's again. And this is useful in a case where like you have an angle, but the angle itself is something that has been doubled. Let's see if I can give you a good example. Like, for example, let's say I gave you the sine of 600. The sine of 600 might not be something useful to us. But what if I wrote it as the sine of 2 times 300? Does that make sense? Well, the reason why that's useful is that this is equal to 2 times the sine of 300 times the cosine of 300. Even though the angle 600 was not something I can really work with all that well, I can work with 300s, because 300s are one of those angles that would be down in like this quadrant here, which we could actually put some numbers to. Anyways, here's the rules for the double angle identities. Sine, cosine, and tan. Now, do you guys, I always forget, do they give you the adaptation ones for the cosine 2a? Do they give you all 3 cosine 2a formulas? Or just one of them? Okay, good. Let me see if I can explain why. This one right here is the original one that was discovered for cosine. But then what they did is they recognized that sine squareds and cosine squareds are part of another identity, the Pythagorean one, which is like sine squared plus cosine squared equals 1. What they did is they took, like, say, the cosine squared to the other side. And then they said, let's take this little bit right here and substitute it inside there. And what ends up happening then is you have cosine squared minus 1. And then you have a minus cosine, which really means that you're adding an extra cosine. And that's where this one came from, where you actually have 2 cosines, because you have this cosine right here and this cosine right here. And then you have a minus 1. Just this little bit right there. So when I first started teaching, I'm thinking that I put this on my slide because they didn't put all 3 cosine formulas on your data sheet. But apparently you have all of them. So you don't have to worry about memorizing those other ones. So, anyways, let's skip ahead here. Let's do some of the diploma questions. I think that's probably where we need to start. I feel like, I hope I'm right on this, I feel like you guys have an idea of how identities are supposed to work. Really, the key now is just, can we use them to solve problems? So let's try some. As I look at this one right here, I need to try to find something similar looking to cosine squared minus sine squared. Can you find anything on your data sheet that involves cosine squareds minus sine squareds?
Sine squared plus cosine.
That'll work. The Pythagorean one, the one that equals 1, that might work. I'm not sure that any of those are going to fit what we have for A, B, C, and D, though. But there is another one. I think you just mentioned it.
Cos 2a is equal to cos 2a sine 2a.
So cos 2a is equal to cos 2a. Oh my goodness, I can't write anything proper today. The cosine of 2a is equal to cos squared a minus sine squared a.
Yeah.
Does that make sense? So in our example, a must be 4 pi. Because we have cosine squared of 4 pi minus sine squared of 4 pi. So that means this must be equivalent to the cosine of 2 times 4 pi. 2 times 4 pi would be 8 pi. You should be able to type in cosine 8 pi, get an answer. Type in all of this stuff up here, get an answer, and then it should be the same number as well. So you're going to double check. Did you just try that? Did it work? Okay. Did that make sense?
Yes.
Cool. Try another one. One of the ways that they can test your ability to prove identities is, I think I've shown you this before in a different unit, they'll give you a list of work, and then they'll ask you where did they screw up. So they can't actually ask you to do your own work, but they can ask you to double check somebody else's work and find the mistake. So here they have sine squared plus cosine, or sine x plus cosine x, and it's all squared. And then by the time they're done, they get to this point right here, but it's wrong. Somewhere in here they messed up. So we want to try to find where they messed up. So, let's take it from the top here. Sine squared x plus cos squared x. What they did is they went sine squared x stayed the same, and they made cos squared x turn into 1 minus sine squared x. Is this little step right here, is that valid?
Yeah.
It is actually, because there's that rule that says that sine squared plus cosine squared equals 1. And that means that if you pull the sine to the other side, cosine is equal to 1 minus sine, so that's true. So that was true. Here they kept this the same, and they made sine turn into 1 minus cosine squared. So actually that's true. And then it looks like they took 1 plus 1 to give 2, and a negative cosine and a negative sine to give all of this. Actually, their mistake was in step 1. When you take sine x plus cosine, like sine x cosine x, and you square it, and you write it next to each other, you have to actually foil it. We have to do like all 4 terms, and they skipped 2 of them. Does that make sense? This one's really mean because you might not remember to look from this one to step 1, but step 1 is the one where they screwed up. Yeah, they forgot to factor properly. They just squared both of the terms, but they missed the middle terms. Does that type of question, though, make sense where they might ask you not to do the work yourself, but find the mistake? Wait, this is a type of question where I think of it as like a brain teaser more than a math question. I mean, obviously, we're doing this in math, but this is a puzzle more than it's practical. Like, I cannot think of where this is useful in math, but it's a puzzle. Our goal now is to try to find cosine 2x in terms of m. So the first thing I might suggest then is, what is cosine of 2 of something supposed to equal? There are a bunch of different formulas you could use. One of them, I believe, is cosine squared minus sine squared. That's one of them. But there are 2 others. Can you guys help me out with those? Minus 1? And then one of them involves sine, correct?
1 minus 2 sine squared.
Anybody want breakfast? I'm gonna grab you.
Morning. Oh, thank you.
Get those yummy creamy yogurts. Those look the best. Thanks, guys. Sure, thank you. Okay. Well, now that I've identified some different ways that we could try to write cosine 2x, all I'm given is that sine x equals m. So what I could do is I could plug m in for this bit right here, but that doesn't help with the fact that I don't have something for cosine. I could plug in m right here. I'll do that with a different color, though, just to help make that look nicer. Sine x is really m, so I could put an m right here. Or I could try putting an m right here. I think this one right here is the best bet for getting something that's in my, like one of the 4 answers, because this will now be 1 minus 2m squared. And that's it. Does that make sense? This one's a bit more of a challenging kind of question because you really can't use your graphing calculator. Like, you can't really plug in a number because you don't know what x is and you don't know what m is. So you could try making up some numbers, I guess. It also might just be easier if you know how the identities work too, though. So I don't want to discount doing it the way it was intended.
Wouldn't those first 2 not work anyways?
Well, like this one right here doesn't really work because I don't have something for cosine. And this one right here, again, I don't have something for cosine. So really the only one that would work is the third one. Okay, well, here's one similar to what we were doing yesterday again. Here's an equation. Let's try to figure out what it's equivalent to. Do you have anything on your formula sheet that gives you cosecant to the 4 minus 1? Anything similar to that on there that you can work with? Not really. Okay, so another trick that you can play beforehand here. Do you guys see how this is to the power of 4? That's an even number. It's actually a square rootable number is probably the better way of putting it. And 1 is also a square rootable number. This is a difference of squares. You could write this as a cosecant squared x plus 1. And then you can write it as a cosecant squared x minus 1. Sneakily, they hid in a difference of squares. Now is there something kind of similar to your formula sheet? Because I believe there is something on there involving cosecant squareds. And which one is it? Is it the plus 1 or the minus 1 that does it? Minus 1? So then the one with the minus 1, you said that would be cotan squared? Okay, so I guess this guy right here is going to be stuck as a cosecant squared plus 1. But I think I have an answer now, because that's going to be C. I know they're written in the wrong order, but the order doesn't matter when you multiply, right? Okay, here's another one that, in a way, it's kind of like a brain teaser puzzle. You get 2 main pieces of information. You're told that x is 45. And then you have an expression here that we're going to try to figure out which one of these other ones is similar to it. So, yeah, that's gross. All right, well, I guess knowing that x is 45, that's the first thing I can do is I can plug 45 into this equation right here. So I've got the cosine of 45 plus y over cosine y. Any thoughts? I can't just cancel those cosines, right?
We do that as cos A plus B equals cos A equals B minus sine.
I think that's what we should do, yeah. Let's use that rule. So I don't have it memorized. What's the cosine A plus B rule? Cosine A plus B is going to be the cosine A, cosine B, and then plus or minus? Minus, and then sine A, sine B? Did I do that correctly then? The adding cosine rule means go cos, cosine, sine, and then subtract? Yeah. Okay, well, as I look at the answers that are listed in front of me, I mean, none of them actually have 45s in there, but 2 of them have like root 2s and 2s. And I feel like that's a bit of a giveaway because 45 is one of those angles that we can actually do something with. Like if I draw a quick 45-degree triangle here, 1 root 2 is how 45-degree works. So I could say that this cosine 45 is probably a 1 over root. Ooh, that's not really drawn well. 1 over root 2 cos y. And then sine 45 is also a 1 over root 2. Alright. I still don't have any of the answers, but I feel like I'm getting close to either B or D. Those ones feel like I'm getting close to them. Because they involve root 2s. Yeah, like you're talking can we change all of these guys right here then? Maybe rather than writing them like this, I'll erase it and just go right to 2 over root 2 over 2. For both of them. This will just go right there. Like I feel like at this point, I'm fairly confident that it's either B or D, right? That's my guess.
I thought it just combined. I didn't know it was for both. Root 2 over 2.
Well, like anytime you have like a 1 over root 2, if you times by root 2 over root 2, it would give you root 2 over 2. So rather than writing it like this, I'm just going to go straight and write it like this instead. Okay, I have an idea. The top of this thing right here has something in common. Yeah, I can factor that out. I'm going to factor out the root 2 over 2, factor it out, and it's going to leave me with cosine of y minus the sine of y. I also have one more trick up my sleeve here. You know how when you have common denominators, you're able to combine them all into one big fraction? I'm going to undo that. Because you see how this thing is over cosine y? What I could do is I could say that means that this thing was over cosine y and that this one here was over cosine y. I'm going to like break the fraction back up into pieces. It would be like me telling you that you have 1 plus 2 over 3. Well, that's really 1 over 3 plus 2 over 3. I'm undoing the combining step. Yeah, because then the cos y over y is 1. And sine over cosine is tan. And hopefully now you'll agree that it looks like B. That one's pretty challenging. Right? Like that one required way more steps than some of the other ones we did. The other problem with some of these things is that you have to have pretty strong creative algebraic skills where like you can see something and go, ooh, let's try this. Like for example, when I got to this step right here, I recognized that these guys had something in common. Well, that's the trick to it, right? Is that, I mean, you guys have done stuff like this before. If it had been 2x plus 2y, you guys probably would recognize that you can make it 2x plus y. And I know you guys have done that at some point, right? But it's more confusing when you've got cosines sitting in there too. All right. Here's another one where as soon as they make a numeric response, they suck way worse because you can't really guess and check anything, right? Like you have to have strong algebraic skills. Here you've got a cosine squared and a sine squared. I feel like that's one of the things we just talked about earlier today. Like there's a rule for that. Where you have cosine squared minus sine squared. What's it equal to?
Cosine 2.
Fine. So that means that it's a cosine of 2 of whatever the thing there is what the sine, oh, I did that backwards. Cosine 2 of something is equal to cosine of that something minus the sine of that something. What is this something? Kx. Yeah. For us, this is kx. So fancy way of putting this is all of this stuff right here is really the cosine of 2kx.
Isn't that what they have? Oh, no. Like the whole thing?
Just
makes sense. Yeah. So then if this is supposed to equal cosine of x, Brad's correct that the answer is 0.5. The reason being is there's a 2 sitting right here, right? And in this example right here, there's not a 2 sitting there. What we haven't accounted for is that the k can drop that 2 back down to 1. If k was 0.5, 2 times 0.5 would give you 1, which is kind of what you have written right there. So then k was 0.5. Break my little board. Did that logic make sense? Okay. So what we have at this point right here is we've proven that all of this stuff right here is equal to cosine 2kx. Okay. But it is supposed to equal just cosine of regular x. So my question for you is, what is k to make these equal to each other? What value does k have to be to make this equal this?
Oh, I get it.
So you see how this guy right here has a 2k piece sitting right here, right? We kind of don't want that 2k piece there sitting there at all, right? Because this one has an x and that one has an x, so that's good. Right? This one has, I guess, a 1 right there. I guess if you had to do algebra, what I'm really telling you to do is take 2kx and try to find a way to turn it into 1x. Well, I guess what you could do is you could divide by 2 and x on both sides. Divide by 2, divide by x. Those x's will go away. And I've proved now that k would have to be a half for that to happen. So then k is 0.5. Still makes more sense than Keynesian economics.
No, it does not.
Did I say that right? Keynesian? How do you say that word? Keynesian? See, I don't even know how to say it properly. Alright, how much do I have left here? I've got lots of extra questions in there. Do you guys want to keep doing these as a group? Is that worth our time? Or do you want to try them yourselves? Where do you want to go from here? Because that's pretty much all I've got left is just more practice. What do you want? Okay, we can do group. I mean, we've got 20 minutes left today. We can just keep trying more practice. They are. Like, I don't want to lie to you. They are kind of intimidating because this is one of my frustrations as a teacher preparing you for a diploma. I don't know what to prepare you for. The outcome basically says you need to know how to use identities. I feel like I've shown you how to use identities, right? Like, it's easy, but it's hard, right? Like, for me to show you, I've kind of walked you through how they work, right? And now the hard part is, if they give you a problem, can you solve that problem? And who knows what that problem looks like? Okay, let's try one here. It says here, use this identity right here to take this expression right here and simplify it. Well, I think they did this on purpose. They've identified the cosine squared by itself. So I feel like we should take this cosine squared right here and put that in its place and see where it takes us. Does that make sense? So rather than writing this cosine right here, I'm going to write 1 minus sine squared x. And I'm going to keep going. I'm going to write the next minus sine squared x minus 1 plus 2 sine x. Well, these two things here don't cancel, do they?
But the plus 2 sine x.
But this is just a regular sine x, and this is sine squared x. Does that make sense? I think they've done that on purpose to try to catch you in that trap, because this one is a squared, and this one's not. You can cancel these ones, though, by the way. Here's a 1, and there's a minus 1. I'll use another color here.
What about the other sine squared? There's 2 sine squared.
Okay, so the ones in between these, do these guys cancel? They combine. So you have minus 2 sine squared x's, and then you have 2 sine x's. Is that one of my answers? Gross, it is not, is it?
Didn't you... Oh, no.
I'm just going to make sure I write this really clearly. That's not a 2x, that's a squared x right there. Because that's really important to make sure I don't somehow think that that's a 2.
Would you just factor it?
Nice, good catch. So at this point here, I don't have any of the answers, but this is like x squared and this is like x. We can factor. So I'm actually going to factor out everything I possibly can. I can factor out a 2, because all of these things have a 2 in them. All of them have a sine of x. And then let's see what the leftover bit is. This guy right here, if you factor out the 2, that's gone. If you factor out one of the sine x's, there is a sine x left. So that's a sine x. But it has to be like a negative sine x, unfortunately, because there's that negative up front. And then this guy right here, since you factored out 2 sine x, and he was 2 sine x, the only thing left is the number 1. Which is a if I write the terms here. If I just flip the order of those, it's a. Yeah. Do you get what I mean when I tell you, I guess, it's frustrating for me to teach, because like a lot of the skills you needed to use in that question there are really like the accumulation of good algebra skills that you've learned over the last couple of years with me. Oh, like it's hard to, I can't give you like a template and say, do this, do this, do this, and you're going to solve the problem. Yeah. You need good problem solving skills. Alright. Let's try this one. This one looks intimidating. I guess I look at it at first, even without, like there's a lot of information that's just kind of shoved in here. Let's work with what we know. I'm just going to start with just this sentence right here. Tan x equals negative 6 over 7. Stop. I can plot that. Where is tan negative?
S and C.
Yeah, so I can either put it in this quadrant here, or I can put it in this quadrant here. It actually says later on in the question which quadrant it's supposed to be in, though. You guys see that information right here? It's telling you that x is between 3 pi over 2 and 2 pi. So that indicates to us that we need to actually plot it in this quadrant here. And I should be able to do that then. So tan is the opposite over the adjacent. And I think while I'm at it, I may as well find that hypotenuse, because I'm gathering that hypotenuse is either going to be 85 or 21, seeing as those are some of the square root parts of my answers. At least I'm hoping. Yeah, it's root 85. Does that make sense so far?
Wait, what's the top one? 7?
Oh, that's a 7, yeah, because it's 7 and negative 6, and then this hypotenuse is 85, or root 85. Let's stick with Christmas colors, I guess. Now this piece of information. We need sine to be negative. Again, according to the cast rule, sine is negative in T and C. I could plot them in both triangles, I guess, but again, if I look a little further on in the question here, it lets me know which quadrant we actually care about, so we're again in this fourth quadrant right here. Okay, what is sine? Sine is opposite over hypotenuse. So that means I should be able to find the adjacent, and I bet you good money is on it being root 21, just looking at some of those possible answers there. It'll be 25 minus 4. Yeah, it'll be root 21. Does that make sense so far? Okay, I haven't even actually looked at what the question's asking me for. I've just kind of used the information they gave me to kind of get a start. It now wants to know the exact value of secant x plus y. Okay, well, we actually kind of did this today a little bit, only we never did it with secant. But what is secant related to? Okay, so the same rule applies then. We're going to do the cosine adding rule, only we're going to do secants and cosecants everywhere. Does that make sense? So this is almost like a cosine with a minus 1. Basically, it means that we need to flip all of our fractions upside down. So what's the cosine adding rule?
Cos A, cos B minus sine A.
Cos A, cos B minus sine A, sine B? Is that right? Okay, the only issue here, though, is that we're not actually using cosine, we're using secant. So every single one of these things, when we write out its a ratio, I'm going to flip them all. Does that make sense? So rather than actually finding the cosine, I'm going to find the secant. And rather than finding the sine, I'm going to find the cosecant. Does that logic make sense? So this triangle right here, I think, is the x one, which is A. And this one right here is the y one, which is B. So if I need the cosine of the first thing, which is x, cosine of this triangle is going to be the adjacent over the hypotenuse. I just realized, though, we had to flip that. So we need to do the hypotenuse over the adjacent. Does that make sense? Then I need to pick the cosine out of the other triangle. And so over here, the cosine would normally be the adjacent over the hypotenuse. But again, I've got to flip this. So I've got to make it the hypotenuse over the adjacent. then back to the first triangle. We need the sine of this, but again, I gotta flip it upside down though. So flipping this upside down makes it the sine of A. So normally that's opposite over hypotenuse. We'll make it hypotenuse over opposite. And then for B, normally sine is supposed to be opposite over hypotenuse. But we're going to do hypotenuse over opposite. Does that make sense so far? All right, I'm going to write this down here because we need to clean this up here. We've got root 85 with a 5, and that's all over 7 root 21. And then we're subtracting another 5 with a root 85. And that's all over a 12. Yeah, the problem is these guys right here don't have common denominators though, do they? I just realized something though. Actually, I think it is D. You know how I flipped all of these fractions right here? What if I didn't flip them though? What if I had left them all the same and then flipped them later? Like what I'm trying to get at here is, let's say that all of these things before I had flipped them, let's say that it had actually been 7 root 21 over 5 root 85. And then we minus 12 over 5 root 85. What if we hadn't have flipped them? Could we put the denominators together then? Yeah, we could. So then it would give us 7 root 21 minus 12 over 5 root 85. And now flip it. I think that makes more sense. Because if I flipped it earlier, it still works, I think. It's just this work that I have right here. I have to try to find a way to make these guys common denominators. I think it makes way more sense to flip this guy now. So now it's going to be 5 root 85 over 7 root 21 minus 12. I think that's probably more appropriate. So my little note here. Here I'm going to write we flipped too soon right here. And then, so I went back to what it was originally, put them together, and then flip. Probably makes the most sense. Does that make sense? The challenging part, I think I've said this with you guys before. In math, I kind of think of 3 levels. Level 1, you don't know what you're doing, and like when I explained that to you, it went over your head. Level 2, you understood that. Level 3, can you do it yourself? All right, that's the hardest part, right? Is can you do it without my help? To be honest, as I was going through that, like you were getting my, like I haven't done this obviously in a full year, so I didn't remember how to solve that one. Those were the steps that I was going through in my head, going, okay, well this is what makes sense, and all of a sudden I had that, I don't know, like a light bulb moment as I was right here going, yeah, this is gross. And as I look at the answers, I think a couple of you guys recognize, boy, that sure looks like D though. So then, like, is there a way that we can turn it into D? Try one more. Call it a day. This one looks really similar in terms of kind of what we're doing. Yeah, let's give it a try. Sine is 7 over 8. Okay, so if I draw a triangle in this quadrant here, that would be opposite and hypotenuse. By the way, I'm putting it in this quadrant right here because it tells me that A and B are acute angles. So I know that it has to be in quadrant 1. So I just want to figure out what this other side is going to be then. 8 squared minus 7 squared. I got root 15 right here. So I'm just going to make this triangle A, and I'm going to put that in black, and I'll use another color for the other one just to help keep this straight. It says it's an acute angle. So as an acute angle, it's got to be like a less than 90 degree one, so it can't go in these quadrants because those angles are too big. And then when I want to plot b, it says cosine of b is 4 over 5. So that's the adjacent and the hypotenuse. And I know this one. That one's a 3. So it's that 3, 4, 5 triangle. Does that work so far? Now let's actually get to the question. It wants cosine a minus b. I feel like I've asked you this probably 4 times today, but what's the cosine a minus b formula? Cos a, cos b. Minus or plus?
Minus.
It's plus.
Yeah, you add it.
So when you have two things minused in the cosine formula?
Yeah. I was looking at the wrong one now.
Okay. You guys have the formula sheet in front of you, so are we in agreement that's the right formula? Okay, make sure you get the right formula, obviously, because that buggers everything up. Okay, let's try this. Cosine of A. Here's my A triangle. The cosine of A would be the adjacent over the hypotenuse. Then I need the cosine of B. So in the B triangle, the adjacent would be 4 and the hypotenuse would be 5. I am starting to see where this could go. 8 and 5 on the bottom is a 40. I feel like C and D are our best bets here. Actually, C looks really promising because the top is literally 4 root 15. That's what the top right there is. So let's try the other side here. So then we got to do sine of A. Sine of A is going to be your opposite over your hypotenuse. And then in sine of B, it's also your opposite over your hypotenuse. Definitely C. You can start seeing it come together, right? Because this is 4 root 15. This is 21. And they both conveniently have the same denominator of 40. Whoa, 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 whoa. Don't do that.
You know already.
You circled the wrong one. You ever done that before, though? Oh my goodness. All right, why don't we call it there? One last thought here. I just want to show you the outcomes that I'm supposed to teach you one more time, just so you know what they are. And then we'll take off for the weekend. Okay, so here's the outcome I just taught you. You need to know how to prove trigonometric identities. It's very broad. So I liken it to puzzle solving or like, I don't know, brain teasers. The more practice you can get on this stuff, the better you'll be. So I know I skipped a bunch of those diploma questions. Try those at some point. Maybe we should sit down and have a conversation about how to solve the ones we didn't do already. Does that work? Okay, next week I believe the plan is workday, quiz, workday, quiz, workday.
Oh, that's nice.
Yeah. So I believe the plan is basically, no, actually it's workday, quiz, review lesson. We're just doing like a recap lesson of what we've talked about. So workday, quiz, recap lesson, another quiz, workday, and then next week, Monday, not next week, but the week after that Monday, unit test. So basically we're at the point now where we're going to write a bunch of tests. But hopefully you'd agree with me, like this is one of the best ways you're going to learn is just to write tests.
Yeah.
You know, like I'm just going to give you 75 questions to practice now, right? 3 tests of 25 more or less. And that's a good way to help you learn. Questions, comments, concerns, conundrums, curiosities, complaints, criticisms? No one actually ever says anything when I ask that question. You just all smile and go, hey, that's clever. You guys good? All right, have a good weekend. See you guys later. The bell's going any minute, so.